Okay, so our next speaker is Professor Boris Kunyavskii, who has kindly agreed to give a series of lectures, a series of 4 lectures. I'm sorry, in one of my email I said 3 lectures, so there was some confusion. So it's a series of 4 lectures, and he's going to talk about word maps on algebraic groups. Professor Kunyavskii, you can begin
Thank
now.
you. I'm
Yeah,
happy to
yeah,
see you all here. So first, a couple of words before I start sharing my screen.
sure.
In this mini course, I'm going to tell you something about the topic in the title. I do not pretend to give you a comprehensive picture. Rather, I want to present my personal view on this area. So you will see some overview of the area. You will get some classical statements, some simple examples and more difficult examples, maybe some exercises. I will give some proofs, not many of them, but a couple of main results will be proved, or sketches of proofs will be given. In most cases, I will omit proofs and will give just a survey. So some results will be very well known and classical. Some results will be more recent. I will also talk about some relatively new results, and also I'll try to give as many as possible open problems to give some, say, insight for your eventual future research. So let me just start with sharing my presentation, and of course you are very welcome to ask questions. Maybe in chat it will be more visible, but also in the course of the lecture, it's no problem. So let's start. Sorry, one moment. I'll try to. One moment. I have some
Sure, sure,
technical
no problem.
problems here.
Yeah,
One moment.
yeah,
This system is relatively new for me. I'm usually using
right.
Zoom, so
Yeah,
it's similar but a little bit different.
yeah, yeah.
So that's it. I hope it's visible now. It's the title of the series of lectures.
Yes.
And first, let me describe my main motivation for working in this area. So my main theme, maybe it's not the main theme for other people. For me, it's important to understand how equations in groups are related to equations in associative algebras. And informally, what I want is to construct a sort of bridge between these two areas, which are related, but not as closely as I would wish. And I will be more modest for the reason which will be explained later. I will restrict my attention to equations in simple or semi-simple algebraic groups. And on the other side of the bridge, I will look at equations in matrix algebras. And also there is a related third side of the bridge, if I could say this. The Lie algebra structure is also important, so I will also talk about equations in semi-simple Lie algebras. So let me start with a typical example. So we consider the algebraic group SLN of n by n matrices with determinant 1. And I can attach to it the associative algebra of matrices with trace 0 and operations of multiplications by scalar, matrix addition and matrix multiplication. And also I can consider the Lie algebra with German SL of n by n matrices with trace 0 and the operations of multiplication by scalar as before, and Lie bracket. A comma b is given by the usual commutator formula, a times b minus b times a. Yeah, that's a typical situation. Okay. So now I told you that I'm going to speak about equations. So what do we mean by equations? I mean general algebraists. Yeah, there are many other people in mathematics, and not only in mathematics, who are interested in equations. But we think that equation is an expression of the form which is written here. So the equality of two expressions where there are two kinds of letters here. You noticed A, B, C, and X, Y, Z. Traditionally, by A, B, C, and so on, we think something constant. And this means that we fix some elements of some algebra, which is our universe where we live. And on the contrary, X, Y, Z, and so on are unknowns. Yes, and then it's not a rigorous definition, but that's what we all think about. So this means that unknowns means that we can substitute elements of our algebra instead of these symbols. Yeah. So if you prefer Hebrew language, then we fix a set of generators of the free algebra FA, build on our algebra A, in some fixed variety of algebras containing A. Say we can consider a variety of groups. It's a typical situation in this lecture today. So what can be said about P and Q? P and Q are, so to speak, polynomials. Well, it's informally. Formally, these are elements of this free algebra. Or, in simple words, we consider expressions which contain signs of operations which are allowed in our class of algebras, and which are subject to laws of the corresponding variety. For instance, we consider abelian groups or commutative algebras, then we always identify xy and yx. Yeah, that's in the algebra, it's different. So each time we fix the laws of the corresponding class of algebras of this variety. Let me say something very important that you and I, in this lecture, mean by equations something different, something much more restrictive. We only consider a certain class of equations which are of the form which is written here. So this means that The right-hand side is not an arbitrary expression, but we fix some element of our algebra. P is polynomial as above, but also, look, we do not allow constant entries on the left-hand side. Unless stated otherwise. Today, I will only consider this class of equations, but later, at some point, I will also say something about equations with constants. But as of now, it is not allowed. Let me explain this by examples. So, if we consider a matrix algebra, then we are allowed to consider equations of the form xy minus yx equals c, but not bx minus xb equals c, or say quadratic equation ax squared plus bx plus c equals 0, where a, b, c are constants, as we agreed. So the first equation is legal, and the two last equations are illegal for us as of now. So not that they are not interesting, they are very interesting. And in fact, very much can be said about quadratic equations, surprisingly much interesting things, but as of now, this is not permitted. We restrict ourselves to a very specific class of equations. Now, another important assumptions or restrictions or limitations. Where do we seek solutions? It's also a little bit ambiguous. There are several options, and here we are also very restrictive. Solutions are only sought in A, so in the same algebra A, and not in any larger object. Let's go closer to our setup, to groups. So suppose we work in the variety of groups. We fix the right-hand side A of our equation, and we look for x, y, and so on in G such that this equality holds. So x, y, and so on are sought in G and not in some overgroup, not in some bigger object. Well, also, I cannot say that the other option is not interesting. It is, and it is a fascinating area of research which goes back to classics, to Bernard Neumann, who wrote a paper about this in 1943. And you can find several modern surveys in the papers by Romankov, 2012. By the way, if you will be interested in precise reference, just send me an email and I'll give you. And also another paper by Anton Klitschko and Andreas Tom, 2017. They consider equations over groups, usually a standard abuse of language. How can one recognize what we are talking about? People using my context say equations in groups, and the other option is usually encoded by equations over groups. Yeah. So we consider only the first option, equations in groups. Yeah. And let me describe main questions we are interested in. Well, given a polynomial, is the equation solvable for all right-hand sides? Yeah? For any A, or at least for a typical A. There is some important ambiguity I'll discuss below. And also, informally, does it have many solutions? Everything will be formalized later, but as of now, I want to give you a naive viewpoint the situation. Also, in one of the forthcoming lectures, I will consider some cases where our group or algebra is of arithmetic nature. So some number theory is involved, and I will be interested in good, this will be formalized later, local to global properties of the set of solutions of these equations. Yeah. Also, it's interesting to know, does the set of solutions depend on A? This is the next question. Or if yes, to what extent? This can also be formalized and also will be discussed later. So I'm going over to group case. If as of now you have some questions, please go ahead.
So, what do you mean by variety of groups?
By
I'm
algebraic
just.
group, I will mean, well,
No, you said variety of groups. Variety
sorry,
of groups. Variety.
please say it again, I can hear you.
Uh, uh, you said somewhere variety of groups.
Yeah, variety of groups. Variety, I mean the class of groups which can be defined by certain laws. So you write down axioms of groups, say the existence of unit element, the existence of inverse element, and associativity law. And this is what's usually called variety. In the same flavor, I can talk about variety of algebras, of Lie algebras, for instance. So it's in the sense of universal algebra.
Okay.
So you have some set with operations, one or more operations, which satisfy a certain set of axioms, which can be written down by, say, as in groups. I don't want to give precise logical definitions, but informally, that's what I mean here. Okay? And if you have a variety, you can consider the free object in this variety. Say a free group is something which can be defined by generators, a finite set of generators with no relations, only axioms of groups. Yeah, and the same can be said about the variety of Lie algebras, say only anti-commutativity and Jacobi identity hold. And in the same spirit, I can speak about free objects in any variety in the sense of universal algebra. So this is some general frame for groups, for associative algebras, for Lie algebras, whatever. Okay. Well, so let me continue. Now I'm going to groups. Once again, I have the same technical problem. When I stop sharing, for some reasons, it's difficult to return.
Right.
Oh, well, yeah, I think now it's okay. Well, so group case. So now I consider an element W of some finitely generated free group on D generators. So you think about this as a word in the xi, in the generators, and also in the inverse. And also we fix some group G. And the questions I considered earlier are formulated in exactly the same way here. So we consider the equation which is written, w of x1 so on xd equals g, and we fix w, and we ask ourselves whether this equation is solvable for all right-hand sides, or at least for typical right-hand side. What's typical is to be discussed. Now let me consider some very simple example to warm up. Well, to warm up symbolically, it's warm, very warm in our place, and I suspect that in your place also, but to make people awake and to prepare them for the forthcoming series of lectures of Anupam on power maps. So let me just start with sort of quiz. So what do you think about this equation in SL2R? R stands for real numbers. We consider the equation x squared equals g. What do you think? I do not ask you to give a proof or to argument, just intuition. Is it always solvable or not? Just say it. Several people can say I'm not going to make statistics. What do you think? Yes or no? Just
no.
No. Yeah, you have correct intuition. Yeah, here is an argument. So consider, whereas there are many counterexamples, of course. I consider the following matrix, diagonal matrix with entries -4 and -1/4, and assume to the contrary that there exists some matrix H whose square gives us G, then, well, by Jordan's theorem, say, one of the eigenvalues of H is plus minus 2i, I square root of -1, and the other is plus or minus I over 2, but this cannot happen because the eigenvalues must be conjugate because the characteristic polynomial has real coefficients, because our matrix, original matrix, is real. So we have an example of non-solvable equation. So this makes the situation non-trivial. Now, the next question, can one improve the situation by replacing R with C? So replace real numbers with complex numbers. So is the same equation, x squared equals g, always solvable in SL of 2C? What do you think? Once again, intuition, yes, no?
It's not even in this case.
Okay. Here is the answer. The answer is still no. Here is a counterexample. We consider the following upper triangular matrix. We assume to the contrary that H square, there is H such that H square equals G. Then again, by the same Jordan's theorem, its eigenvalues must be either both equal to I or both equal to minus I. Yeah? They must be equal. One Jordan block is seen here. And in both cases, we have the determinant which is equal to -1 and not to 1. So it's contradiction. Again, we see that the equation is unsolvable. Are there other ways out? Well, there are some. We want to improve the situation to make our equation solvable. And here is the first way. We factorize out the center, plus -1. And we consider the group, which is called the projective special linear group, PSL of 2C. And here, what do you think? I gave you a hint, of course, about this equation. What do you think? Is it also always solvable? Yes, no? I don't hear.
Yes, yes.
Yes, it is yes. Indeed, it is yes. I don't want to prove this. I'll return to this group in one of my forthcoming lectures because this situation is deceptively simple. There are many subtleties here, but the answer to this question is indeed yes. And moreover, for any power n, for any exponent n, and for any rank of this group, any size of matrices, one can prove that the power equation is always solvable in the projective special linear group. And can one generalize further and ask about the same power equations for any connected simple algebraic group of a joint type? A joint means that we factor out the center as here. And here the intuition may be deceptive, because here the answer is no. It's by no means obvious. Maybe in India people know more about that because one of the main contributors to the area is a mathematician from India, Pradeep Chatterjee. Together with Robert Steinberg, in fact, independently, Steinberg and Chatterjee proved the following theorem: that the power map is surjective. Here, K is an algebraically closed field of any characteristic, say, characteristic exponent P, I'm saying. If and only if the power, the exponent, is prime to P and also prime to order of the center and prime to all bad primes. I'm not going to make this more precise. Maybe Anupam will say more. Anyway, it's not in the streamline of my course. Bad primes are, well, usually 2, 3, and 5. 2 is always bad. 3 and 5 are bad for some of the types of groups. But still, we see that there are highly non-trivial situations here. Now, let me mention another way out, which is also important. Instead of our split group, say, such as SL, we can consider its compact real form, as in Lie groups. Say we can consider the unitary group, which is a compact form of SL. And then one can use the following classical fact from Lie theory. So we can consider the exponential map from the Lie algebra to Lie group over R. We consider real points. And it's classically known, it's a non-trivial theorem in Lie theory that this map is surjective. And then we can prove that any power map on such compact group is surjective. Here is the solution. Say you divide over n, and you consider, you take the exponent, and then you consider the nth power. So this is the way out. Why did I want to mention this? Because surprisingly, this method replacing, well, a simpler group in a sense, a split one, with its compact form, have many advantages, and some of them will appear very soon, already today. Well, Now I reformulate my questions in a little more highbrow language, and I'm going to introduce the object which appeared in the title of my series of lectures. What is word map? So I fix a word in D letters as before. Well, let's assume for a moment that it's non-trivial in the following sense, that it is not a proper power of some other word. And let's denote by the same letter W the evaluation map. What does it mean? So you consider any D tuple of elements of our group G, and we just substitute G1 instead of X1, G2 instead of X2, and so on, GD instead of XD. Then you perform all operations which appear in our word. So you raise to all powers and perform all multiplications. And as a result, you get another element of our group G. And that's is defined as the value of our word. So we consider a map from the dth power of G to G. Just a map. It's not a homomorphism. It's an important thing that one shouldn't be too optimistic. It is almost never homomorphism, except for the case of commutative groups, which is not that interesting. And it's a map. It has some good properties, some not so good properties, but it's almost never a homomorphism, but it is related in a straightforward manner to the questions we posed. Namely, we rephrase our questions about the existence of a solution to our equation for all right-hand sides as follows. We ask, is W surjective when, say, we are over C and G is of a joint type? We understood that this assumption is important because otherwise we immediately arrive at counterexamples. And the second type of questions of setup, we consider the field of real numbers, and we consider compact groups, and we ask the same questions. These questions looks natural, looks simple, but they are not. In fact, surprisingly, the first question is wide open. No counterexamples are known. There are some surjectivity theorems in special cases, which I will present later. But as I said, it's wide open even in the simple case PSL of 2C. As I told, this question is deceptively simple, and we'll discuss this later. As to the real case, there are counterexamples, relatively recent, and they will also be discussed. Let me just give a hint to what's known to give you some impression. A typical good case is given by a theorem by Nikolai Gardzeev. Let's go in the direction of commutators and slightly general words, say iterated commutator. I call it an angle word. Then we know then the image of such a word contains all semi-simple elements and all unipotent elements, but in general, it's not known whether it's surjective. So you see, even in such simple situations, there is no answer, and there is a place for research. And one can deduce from this, I'll tell you the whole story when we'll discuss this special case PSL of 2C, that any angle word is surjective on PSL of 2C In fact, it's obvious right now because one has to uh, remember that this group is very special in the following sense. Each element of PSL is either semisimple or unipotent. So this corollary is immediate from Gurdjieff's theorem. But there are also other proofs. I'll try to talk about them later. And also there are some other classes of words. There are several more recent works by Gurdjieff with his collaborators, with his students, works by Bandman and Zarhin, works by Yezernik and Sanchez. So also some our joint work with Gurdjieff and Plotkin. I'll tell you something about this case later. Now about real case. Here there are positive results and also negative results. A positive result say something good about angle words as above, that it is surjective on any compact group. First, it was proven by Al-Kasapi and Tom in 2012, and then generalized by Gurdjieff to any compact groups. So Al-Kasapi and Tom proved this for a unitary group, and Gurdjieff proved the general fact. But also another positive result concerns some special classes of words, not really special words, but many classes. So here I denote by F2 to the power 2 the second derived subgroups of the free group F2. So such words are good in a sense that the positive result says that for infinitely many sizes of matrices, such words produce the surjective word maps. What is more striking? The negative results. That was proved by Andreas Thom in 2013, that in special unitary groups, we observe the following phenomenon. Consider the unit matrix. Fix some epsilon. Consider some neighborhood, epsilon neighborhood of your unitary or your unit matrix in some good metric. I'll return to this theorem later. It doesn't matter too much which metric is chosen here. So then, surprisingly, that for any epsilon, one can find a word such that the word map is not only non-surjective, but its image is very small. It's arbitrarily small. It lies in this neighborhood. So the situation is, in fact, very much opposite to what we see, what we have seen before. And this dichotomy also will be discussed in our course. It's a very important phenomenon. Now, let me make some informal considerations before I'll make a short break for questions. So we see this dichotomy. It's the situation which is typical in natural sciences, in physics and chemistry. So sometimes the property you are interested in holds, and sometimes does not hold. So you want to understand what's going on typically in general position, for random element, whatever you call it. Is it typical to be surjective, or is it typical to be non-surjective? In our setup, say chemists, maybe they ask other question: is this material, say, sufficiently good for their goals or not? Typically good or typically bad? So informally, this is the most important kind of questions whenever you are not able to produce qualitative results. And we see that the situation is not easy. For now, we have a dichotomy. We do not understand it as of now sufficiently well. So we can ask the same kind of questions. And I call it Panda principle for the reason I'll explain in the next slide, that a reasonable property of a reasonable mathematical object lying inside a reasonable class of objects may not hold, but it will hold at least for an object in general position, if not always, provided the class under consideration is enlarged or restricted, if necessary, in an appropriate way. I'll give some more concrete examples. We're not philosophers, we are mathematicians. So let me illustrate this by some loose expressions, say in loose terms. This means that the probability of the event that a randomly picked animal is a panda will be much higher if the samples allowed to test are restrictively placed within Sichuan province. That's how I illustrate this. So what do I mean? If you try to pick up a random animal on our globe, it's hard to expect that it will be panda. Panda is a rare animal. You have some also in some regions of India, but say in our places, we have several species in zoos. So the probability is extremely low. It's very unlikely that a typical element or randomly picked up animal is panda. But if we do the same inside the Sichuan province of China, the probability becomes much higher. That's what I wanted to illustrate, that the setup very much has very high influence on the answer to our informal questions. So we have to make more precise what is typical, what is random, what is allowed to do, what's our permitted class of objects. Let me return to mathematics. Say anyone can find lots of examples looking at his or her favorite area of mathematics. Well, my favorite area of mathematics, I could say, where I'm not a big expert, but I like it very much, is number theory. And in algebraic number theory, I can look at finite Galois extensions of number fields. Then the Hasse theorem says, the Hasse principle, I call it, that every element of K which is a norm everywhere locally is a norm globally. Those who do not know number theory may ignore this. It's just an illustration of a general principle. So principle means for me the same as for physicists. Principle is a certain statement which sometimes holds, sometimes does not hold, but is very useful and it's applicable. So what's said is not always true. So for most Galois extensions, it does not hold. But if we restrict our attention to cyclic extension, it always holds. This is Hasse theorem. So we want to modify our setup to make the situation as in our picture for pandas. And I have here to enlarge our areal, and if we allow our extensions to vary among all finite extensions, not necessarily normal, then the Hasse principle holds in general positions. So if we consider any extension of degree n, such that the Galois group or the normal closure is the whole symmetric group, then one can prove that the Hasse principle holds. So you see, the answer to our question depends very much on the original setup. And in fact, one can generalize this for those of you who know what are principal homogeneous spaces. So it can be generalized to generic maximal tori in simple algebraic groups. I leave this remark only for people with more expertise in the area, so most of you can ignore this. So now I want to formulate this as follows. So we are given a certain class of groups. Usually it's not easy, and conceptually it may be challenging to produce a more or less precise setup in the spirit of this principle, so that you can give a definite answer, what is typical, what is random, and the equation is typically solvable. I'll try to do this now. Once again, you should not be over-optimistic, and, well, it may be hard. So when you see these expressions, random, generic, typical, general positions, so in fact, you need to think about precise definition. And it's a long story, and there are many papers on the topic. I mentioned here only a few of them. The notions of a random group or randomly algebras are discussed by Gromov and also by Olshansky, also by Ilyakovich and Shoup. And there are many different approaches to the genericity, and in some cases the answers will heavily depend on your precise definition. So is the situation in our case, and let me explain why. I'm now going over to the culmination of our today's consideration. Maybe the most important theorem in the area is a theorem by Armand Borel, and here is the statement. If you have some field K, and if you have some connected semi-simple algebraic group over K, and you have some non-trivial word, which is not identity, then the corresponding word map is dominant. I'll explain in a minute what does it mean. This means that the image of the map contains a Zariski dense open set. How can one translate this into naive language? This means exactly what we wanted, that for typical right-hand side, the word equation is solvable, because Zariski dense is something big for algebraic geometries. Yeah. So if you pick your panda from some open set, which is Zariski dense, then typically you can say that your word equation is solvable. Let me make a short digression, a nice consequence for your homework, that you can deduce some nice consequence from this. Say, consider the case where K is algebraically closed. Then for such a G, semi-simple connected algebraic group, every element of G can be represented as a product of at most two values of our word map. This can easily be proved. You can take Borel's handbook, textbook, and you'll prove this easily. Do not be over-optimistic here too, because this is not true for non-closed fields. But anyway, this is a, oh, sorry for misprinting exercise here. Well, sorry. Now, I want to continue this long discussion once again before making a short break. That the answer to the question whether panda is typical animal may depend on what do you mean by typical. What do I mean mathematically? I want to return to Tom's contra-example. It means that for some word W, all our pandas, so all unitary matrices from the image of W, live within a small neighborhood of the unit matrices. So if you ask Tom whether these pandas are typical, he would not call them typical. They live within a very small neighborhood, right? But if we ask Borel, Borel probably would. It's no contradiction because epsilon neighborhood is risky dense. So it's a sort of very basic, very important contradiction between viewpoints of algebraic geometers and all other people, say analysts. Because epsilon neighborhood, which is something very small from any person from the street, you could say, yeah, from the corridor of your university, except for algebraic geometers. Epsilon neighborhood is something very, very small, but it's a risky dense. So for crazy guys, as algebraic geometers are, something small for other people is very big. The risky dense for any algebraic geometry is something big. So you see the answer very much depends on viewpoint. There are many other striking examples I usually give to my students about the risky density, that in many senses the risky density is not something good for naive point of view. I return to my favorite area, number theory. Consider the following set of integers. Consider integers that are representable as 2021st powers of some other integers. What can you say about this set of integer numbers? Is it big or small? Well, any guy with common sense will say that, well, it's very small, it's very rare event that your integer is such a power, right? But arithmetic geometry, this crazy person would definitely say, yes, of course, it is a risky dance. So take this into account. So when you ask yourselves such questions which are not very well formalized, to be typical, to be large, to be small, be precise. Define in a precise way what exactly is meant by being big or small. Let's. I want to make a very short break for giving you possibility to ask questions. So, any questions so far? If not, I'll continue. My plan for today, so I will continue with some informal consideration in the same spirit, and then I'll give you a sketch of proof of Boris theorem. It's the most important theorem. The proof is not easy at all, and there are several different proofs, so I'll try to give you a sketch, leaving some details missing for your homework, for thinking. So let's go ahead. One moment. So some more informal considerations. Why Borel always talked about semi-simple groups? Why I'm talking about them? And if you remember on the first slide, I also said that I'll restrict my attention to this class of group. Why I'm so restrictive? Let's see. First, let's note that over-optimistic attempts may fail. If you want to consider arbitrary groups, not semi-simple algebraic groups, then there is a general result, relatively recent, by Alexei Mesnikov and Nikolaev, 2011, that for any W, I'm not going to say what is non-elementary hyperbolic group, that not only the word map is not surjective, it's very far from being surjective. So it has infinite W width. So it's not enough to fix some number of some integer number, say 2021, to represent any given element as a product of 2021 W values. No, it's not possible. So why it's important? Because Alexander Olshansky showed that hyperbolic groups are generic within the class of all groups. So in a sense, if you pick up a typical group, it will be hyperbolic and will have infinite word width. So no hope for optimists. So one has to restrict one's ambitions. Now let's take a more modest attempt. Say, let's try to produce a very small step outside to replace algebraic group with Lie group. And surprisingly, you fail, even for very simple words such as a commutator. Then, if we consider connected semi-simple Lie groups, then it has finite commutator width if and only if its center is finite. In particular, if you consider the universal cover, it has infinite commutator width. This is an observation by John Milner, which was cited in paper Wood, 1971. So for Lie groups, so it's Lie group which does not come from any algebraic group, but it's a good object, but it's bad from the point of view of word maps. Another attempt, let's forget about algebraicity and let's insist on the simplicity of G. And ask, what about word maps on simple groups, abstract groups? And this problem was wide open for a long time. But in 1992, Jean Barge and Etienne Gis discovered simple groups of infinite commutator width. They used highbrow differential geometry, and the title of their paper is the Maslov index, so some differential geometric notion. And groups are groups of diffeomorphisms of some manifolds. And they proved using very advanced technique from differential geometry that the rising groups may be of infinite commutator width. This means that the word map is very far from being surjective. Then algebraists were ashamed that the solutions came from outside, and Muranov discovered some finitely generated examples in purely algebraic terms, and there are many other examples discovered later. But let me mention that some more modest attempts are more successful. We can extend Borel's theorem to some classes of non-semisimple but perfect algebraic groups. Perfect means that the first derived subgroup is equal to our original group. This was done in our joint work with Gurdjieff and Plotkin, and we'll briefly discuss this later. So some small progress is still possible. And there are many interesting counterparts for finite groups. This is a fascinating topic. Unfortunately, I will not have much time to discuss this, maybe little, but you are very welcome to look at the talk of Günter Mali in Bourbaki's seminar in March 2013. So main contributors to the proof of Orer's conjecture, which says that every element of finite simple groups is a single commutator. The main contributors are Erich Ehlers and Nikolai Gurdjieff, who proved this for most finite simple groups. And then the proof was finished in very difficult and brilliant work by Martin Liebeck, Eamon O'Brien, Aner Shalev, and Pham Hut Yep. This is also discussed in our joint survey paper with Tatiana Banvan and Shelley Garrion in 2014, so you are welcome to have a look. Well, now let's go ahead. So in the last half an hour, I'll try to present here the main steps of the proof of Borel's theorem. I will not give all details, as I told you. The proof is not straightforward, though not long. There are several interesting ingredients here. I'll try to emphasize what seems important for me and what will appear in the forthcoming lectures, and what is to be taken into account analyzing the proof. Well, so let's go ahead. So I remind you the setup. So here is our word map, W. We denote its image by I. So by Z we denote its Zariski closure. Well, we want to prove that Z equals the whole G. So start with some obvious general observation. Of course, I contains 1. Why? Because just substitute a d-tuple of elements of G, which are all equal to 1, to the unit element. After raising to all powers and making all multiplications, after performing all these operations, of course, you'll arrive to the unit element. So you'll get 1 as the image of the unit d-tuple. So it's nothing to prove, but this is important. So at least we know some special important element of G, which is always in the image. Now, the next observation, which you can easily check on the way to your house, say that this image is invariant under conjugation. Just make a simple computation. Say, assume that your small g is in the image, and consider a conjugate element by h. If you conjugate all entries of your d-tuples, which is mapped onto your G, if you conjugate each entry using the same conjugating element by elementary properties of operations in groups, you will get the needed result. So as I is invariant under conjugation, you conclude that it is a union of conjugacy classes. Yeah, it's also very simple, but also important, and will be used later. The next observation is, well, it's not completely trivial, but it's some basic fact from algebraic geometry, that the dominance property is compatible with base change. You can find the proof in good textbooks on algebraic geometry, but, well, unfortunately not in every textbook, but it is known. So what do I mean compatible? In precise terms, this means that if you have two algebraic varieties, if you have two algebraic varieties and the morphism between them, which is dominant over the ground field, then it is true after you extend your ground field to some overfield and vice versa. So this allows us much freedom. We want to assume our ground field to be as large as we wish. We can assume that it is algebraically closed if it's important, and at some point we need it to be of infinite transcendence degree over the prime field. So that's what was called by André Weil the universal ground field. So we can use this setup because the dominance property is very good in this sense. Well, now I told you that I'm not going to present the whole proof. So for simplicity, I consider the case of characteristic zero. There are not so many real difficulties in general, but this makes our lives easier as usual. So first, let me consider the very simple case. If we consider words in one letter, then we have a power map. You have only one letter x. So after raising to some power, we assume that the word is not trivial, so n is not zero. We have a power map. We want to prove dominance. We pick a semi-simple element G. According to the general theory of algebraic groups, of linear algebraic groups, it lies in some torus, some diagonal group. We consider our equation, our power equation, and it's a classical fact that it is solvable in T. Our field is algebraically closed, so it's infinitely divisible, so it's solvable in the multiplicative group, and then it is solvable in the product of multiplicative groups. This is in the textbook by Armand Borel. So our G is in the image. So this means that the image contains all semi-simple elements and is thus risky dense, yeah? Because, well, it's well known that almost by definition that semi-simple elements form as a risky dense subset of T. Semi-simple, I want to remind, means that the matrix is diagonalizable. Well, now the main idea further is to employ the existence of a free subgroup. So our G contains a non-commutative free subgroup. Of course, if the number of letters is at least 2. This is a consequence of Tit's alternative, which says that any linear group is either possesses this property or is virtually solvable, so contains a solvable subgroup of finite index. So this means that, say, simple group, such as SL2, SLN, whatever, contains a non-commutative free subgroup. In fact, I'll use a simpler property later, but this is extremely important. We will use it only once in the proof. But why it's important, I'll tell you right now. I don't want to keep this secret, that in near future we'll try to consider analogs of Borel's theorem for Lie algebras. And it's exactly here where the argument breaks down. No analog of this property holds for simple Lie algebras. This will be discussed later, but once again, this property is of extreme importance. Well, so let's start with the case SL2. It will be induction based. I'll tell you that. The proof will go by induction. So first immediate consequence of Tit's alternative is that the image cannot consist of only one element. One is always an image, but there are other elements too. This seems trivial, but it is not, once again. It's not given, say, from above. This is a consequence of a very deep theorem. In fact, of course, this follows from the existence of a free subgroup, because or even from the earlier result of Vladimir Platonov of 1967, he made attempts for proving Tit's alternative, and in fact, he almost proved this, and in fact, his result holds for any characteristic that G, such as SL2 and any simple algebraic group, has the following property. It does not satisfy any identical relation. And assume for a moment that I equals 1. What does it mean? This means that whenever we substitute G1, G2, and so on, GD, the value of our word map is automatically 1. So this means that we have some relation which holds identically for all d tuples of elements of our group. And this is not possible. This was proved by Platonov. Why it follows? This follows from Tit's alternative, because if you have a free subgroup, no identical relations can hold. I told you earlier today that what is free? Free means that only group laws hold, but no other identical relation. So once again, this is a basis. This is a base of our forthcoming induction, that the image is not 1. It contains something else. The next ingredient is totally ingenious. This is the so-called Deligne-Sullivan trick. You see two fields medalists work together to produce this. Well, after you see this argument, it doesn't look too complicated, but it's ingenious indeed. And in fact, two papers, the paper of Deligne-Sullivan and the paper of Borel, were published in the same issue of Exposition Mathématique, Swiss journal. And here it is. So first of all, we are working with SL2. We can find an infinite subfield of our field such that it allows some division algebra of degree 2, quaternions. Well, and one can choose L to be a local or global field. Why so? Because K can be chosen as large as we wish. Once again, I'm omitting some details. Okay, it looks crazy. Why do we need some algebra? Now we consider the group of elements with reduced norm 1, which is usually denoted by SL1 of D. And it is a group which is regarded as the group of L points of some inner form of SL2, which is usually called an isotropic group. So what's the property of this group? It contains only semi-simple elements. Yeah, and it is a group of elements of division algebra. What means in a form that over L, it is isomorphic to the full matrix algebra. D times K is the whole matrix algebra. And we denote by H the image of SL1 under such an isomorphism. Then H is the Zariski dense subgroup of G because our field is infinite. Well, this is the whole point. Why is it better than our original group? I'll show you in a minute. In fact, this trick is reminiscent to the famous unitary trick of Hermann Weyl, who also used the anisotropic forms of split groups, splitly algebras. The word anisotropic did not exist at that time. He called them compact real forms, but morally it's the same idea that to some extent compact forms are better than split forms, and to some extent anisotropic groups are better than split groups. That's what I showed you earlier today. Now, concretely, take any non-identity element small h from our capital H. Then I claim that none of its eigenvalues is equal to 1. Why? Consider h minus 1. H is different from 1, so h minus 1 is non-zero, but we are in the division ring, so it's invertible. All non-zero elements are invertible. Hence, it has no zero eigenvalues. Hence, H has no eigenvalues equal to 1. And as a conclusion, our image cannot contain, it contains an element, none of whose eigenvalues is equal to 1. Okay? And it allows us to finish the proof in the case SL2. So I recall you once again that any, non-central element is either semi-simple or unipotent. Just use Jordan decomposition if you wish. Then assume to the contrary that the closure of the image is not equal to the whole G. The dimension of G is 3, so the dimension of Z is at most 2. So where it lies? It lies in the union of the set of all unipotent elements and some semi-simple conjugacy classes. Now, another basic fact from the theory of algebraic groups that semi-simple conjugacy classes are all closed. Then, of course, they are disjoint from U. So the semi-simple element has eigenvalues lambda and inverse of lambda. Yeah? But we know our obvious remark that Z contains 1 because I contains 1. So this means that Z cannot be inside any semi-simple conjugacy class in this disjoint union. So this means that Z is inside U. But all unipotent elements have all eigenvalues equal to 1. And this contradicts the conclusion of the previous slide of the Deligne-Sullivan trick. And so we are done in the case of SL2. The induction base is finished. Yeah, it's a very nice argument. Once again, it totally breaks down for the Lie algebras, which will be discussed next week. Now, induction step. It's also not straightforward. First, we want to go over from SL2 to SLM. We proceed by induction here. And let's consider the characteristic map. What does it mean? Some linear algebra, which you all know, and maybe some of you teach linear algebra as myself. Teaching linear algebra is very useful. So consider some a matrix from SLN, consider its characteristic polynomials. I wrote signs as I wrote, but it's not very important. And define the image of G as the collection of n-1 coefficients. Yeah, the last coefficient is the determinant, the sign determinant, -1 to the power n, as you know. So characteristic polynomial does not depend on the representative of conjugacy class. It's conjugate on conjugacy classes. Now, the fibers are single conjugacy classes if we consider polynomials with non-zero discriminant. Now, the image is a union of conjugacy classes, as we observed earlier. Our second trivial observation was such. And so a short argument shows that it contains a dense open subset. That's what we want. If and only if its image under chi-n contains a dense open subset of the affine space. It's just technically easier to consider dense open subsets of this affine space. And by induction hypothesis and the inclusion, we can conclude that the Zariski closure of the image of I under this characteristic map contains a dense open subset of this hyperplane. In fact, it contains the whole hyperplane, but why dense open? It contains all elements of SL n-1. What do I mean? You embed SL n-1, putting it on northwest block of SLN, and putting 1 on the southeast block. Yeah, block diagonal matrix. Then any matrix from SL n-1 is inside the image, and why the risky closure? Because you want to consider determinant 1. So this is left to discuss this. It's a simple argument, in fact. Think about this. How to finish the proof now? Now, a little more algebraic geometry. Our SLN is connected. What does it mean? It's just a terminological issue. This means that the underlying variety is irreducible. If you consider this a risky closure of the image of some morphism of a reducible variety, it is irreducible. Yeah? Now we have to prove that the closure is the whole affine space. This will prove that our map is dominant. So we need to show that there is some element of chi-n of I which is not in our hyperplane. How can we translate this? That there is some matrix C in the image which does not have 1 as an eigenvalue. You noticed, so let me return. What's this hyperplane? How I defined it. Here is our Y. We substitute 1 in our characteristic polynomials, and we have this equality on coefficients. Yeah? So if 1 is not a root of characteristic polynomial, so if it's not an eigenvalue, then this expression is not 0, so it lies outside of our hyperplane. We want to find something outside an irreducible closed subset, and then we'll have, this is hyperplane, so it's of dimension n-2, closed subset of dimension n-2 union with something. The closure will give you the whole affine space. Yeah? So how do we make this step? Another argument is needed here, and there are several ways to prove that. First, in the original proof, there is the Lin-Sullivan trick once again. But I want to show you another one, which is due to my collaborator, Kanel Belov. So Alexei suggests a proof using generic matrices, which shows once again close relation of group structure with metric structure, with associative algebra structure, which is a way to construct bridges I mentioned in the beginning of my talk. So what do I mean? You can consider some independent commuting indeterminants, use them as generators of some polynomial ring, consider matrices of these indeterminants. That's what is called the ring of generic matrices, invention of Shimshon Amitzur. And it's enough to prove that the image contains a generic matrix with the needed property. None of eigenvalues is 1. Well, genericity allows you to use specialization, and this is legitimate because we assumed that K is of large transcendence degree, and we can specialize our generic matrices, replacing them by concrete matrices. And in such a way, we obtain a Zariski open set of needed matrices. So we are looking for generic matrix with this property. Well, assume to the contrary that a generic matrices is not of this property. So it has an eigenvalue 1 according to this assumption. Then its characteristic polynomial is divisible by t minus 1. It's linear algebra, Bezout theorem. And then we use the Cayley-Hamilton theorem, which we all know, which we all learned, which some of us taught, which gives you that this is a annihilating polynomial. So C minus identity matrix times something is 0. But this is a contradiction with a theorem of Amitzur, going back to 55, which states that the ring of generic matrices is a domain, no zero divisors. So here is a beautiful short arguments. So now we know the theorem for SLN, and the last 3 minutes to finish. Any group, not necessarily of type A. Here is a brute force argument. We use the lemma, which says that in such a case, there is a maximal rank subgroup of type A, not necessarily reducible. This is very explicit. I present here inclusions which are to be thought of. Here are hints that I use here. In all cases, C is symplectic, contains n copies of SL2. Now, B and D are spinor. It also contains several copies of SL2. Here it is. And exceptional groups are treated also case by case. In each of the cases, you also see several copies of groups of type A. A brute force argument. Why it is good? We are finishing. Now let G be simply connected. We find the subgroup of the same rank with components of type A. Now, the point is that because the ranks are equal, the groups have the same collection of maximal tori. So by induction, we know that, so by preceding case, we know that the restriction of our map to groups of type A are dominant. Hence, its image contains a maximal torus of G0, then the maximal torus of G. Here one should put G0 to the power D. And then it contains all semi-simple elements of G, which, as we know, form a dense Zariski open subset. So W is dominant. And the final arguments are very easy to go over from simply connected to arbitrary and from simple to semi-simple. There is another misprint here, sorry. This is left as exercise. Try to think about this proof. look at the original paper of Borel, a follow-up paper by Michael Larson, our joint paper with Cannell, Belov, and Plotkin, whatever else. Do not hesitate to write me emails regarding this. And to finish, a short trailer of what will follow. We will start the next lecture by looking at infinitesimal analogues, going over from G to Lie algebra and vice versa. It's a short illustration where we think about one direction as easy and smooth and the opposite one as difficult. I think the second picture is from Himalaya somewhere. You know better than me. And I stop here to answer your questions, if any. I'm sorry to be 1 minute over time. So, questions, remarks, criticism, whatever.
Thank you.
Please tell me if it's too quick, if it's too slow, too boring. I'll try to adjust the speed to your level. And also do not hesitate, well, to use this week for analyzing this proof. In fact, this is the only difficult proof I'll show you, almost in full, because frankly, there are not many deep results of such generality in the theory. Still, after several decades after Borel's work, almost 40 years passed, but the theory, in my opinion, is still in its embryonal state, because there are not so many structures behind the existing proofs. So there are many things to be understood still. Well, if
I had just general question,
yeah.
You were considering Engel words.
Sorry?
Angel words. Do we have? I mean, do we study that for Lie algebra also? I will write in the chat.
Sorry? Can you say it more loud? It's for some reasons I do not hear you.
I will write in the chat. The question I will write in the chat.
Yeah. Please write in chat. Yeah. Yeah, Engel words for Lie algebras. Yeah, for Engel words for Lie algebras, it's okay. For simple Lie algebras, we showed that the corresponding map, well, polynomial, Lie polynomial is surjective. So Euler's conjecture for Lie algebras, in fact, is very easy and classical. If you look at single commutator,
right.
If you look at simple finite dimensional Lie algebras over algebraically closed fields, it's true. Right. And it's classical due to Gordon Brown, but I'll tell something about eventual generalization. It's wide open if you go further, if you want to consider simple real Lie algebras, which are not necessarily split or compact. The analog of Euler's conjecture is open, is wide open. And also, it is wrong as soon as you allow yourself infinite dimensional simple Lie algebras. This is not yet published. This is our recent work joined with Andrei Regeta and Adrien Duboulou. This exists as an archive preprint of this year. So as soon as you move a little beyond the class of simple Lie algebras, the question becomes difficult, very difficult. More questions?
So yes, I have just one. So in the proof of this Borel's theorem, How do you know that image is not 1 using a Tits alternative? What is the argument?
The image is not 1. What does it mean? That you consider your word map. A
Okay.
priori, it is not obvious whether such a pathological situation can happen. You substitute any d-tuple in your word, and eventually the image is always the identity matrix. It seems crazy and impossible, and in the case of groups, it's impossible indeed. But it's not easy to prove this. Once again, this is a consequence either of Platon's theorem, that there are no identical relations in simple algebraic groups, or of even more powerful result of Jacques Tits, that any simple algebraic groups contains a free algebraic subgroup. Whenever you go over from algebraic groups to Lie algebras, something counterintuitive may happen. Consider 2 by 2 complex matrices with trace 0, SL of 2C. Trace 0 complex 2 by 2 matrices. Then you can find some Lie polynomial, which consists of commutators, some iterated commutator, which I will show you next week, such that whenever you substitute any tuple of elements of SL2, any tuple of 2 by 2 trace 0 matrix, the value will be 0. It's something completely, totally counterintuitive, and such polynomials were not known to classics. Say, Lie did not know, Engel did not know, even Jacobson did not know that. It's a development which is mainly due to two people, one in US and one in Soviet Union. Incidentally, both chess masters, because the construction is very far from obvious, combinatorial constructions. These guys are Edward Formanek in US and Razmyslov in Moscow. Yuri Razmyslov, who wrote a book on polynomial identities. Completely counterintuitive examples which turned around our, say, understanding of Lie algebras and the situation there. And this makes a big difference, and it's an essential problem, which is not just a technical one. Well, more questions? Well, if not, have a nice continuation of the day. And well, maybe it's sort of end of your weekend, which is was a working day for you. In our place, Sunday is a usual working day. It's different. And see you in a week. Bye for now.
See you. Thank you.